can't even talk and even announce everything. What did I announce about this?
Okay. So today we are going to look at probability, which is part 6. Under this probability, we have binomial distribution. Okay. So as a matter of introduction, I'm saying this binomial distribution, you find that it applies to situations where elements of the population are classified as either having or not having a given attribute or characteristic. In this particular case, in evaluation of public opinion polls, for instance, electors are either for or against a given candidate or party. In quality control, on the other hand, you find that inspection of an item can either be defective, it can turn out to be defective or non-defective. So where you have two possible outcomes, that type of situation, if you are considering that under probability, is referred to as a binomial probability. Now we have binomial distribution and binomial theorem. So I want to relate binomial distribution to binomial theorem. So let's look at what binomial theorem is. There was a Frenchman some time back, a French mathematician by the name of Blaise Pascal. Blaise Pascal realized that in binomial expansion, the coefficient of variables followed a certain pattern. He noticed that these coefficients could be worked out as combinations that he arranged in a form of a triangle. And that triangle is what we today call Pascal's triangle. So remember, I did walk you through the counting techniques where we learned or we found that there could be what we call permutations and combinations. So for permutations, we were given to understand that this is where you are trying to find out the number of orderings of elements. You're finding out how many ways can can these elements be ordered or arranged with repetition being allowed. Then that is a permutation, and I showed you the formula for permutation, okay, which is the n factorial divided by n minus r factorial. Okay, that's what we looked at. Okay, then we also looked at the combination. This is where I look at a number of elements and find out how many ways are available in which those elements can be arranged without repetition. So here I introduce you to the formula of combination, where what stood out is that this formula included what we call a correction factor, which is r factorial. So that's what we are looking at. So today, in binomial theorem, we are going to make use of this formula combination to find out the number of ways. So that is incorporated by this that was incorporated in the formula by this Frenchman, Blaise Pascal, in what we now call binomial theorem. So the Pascal's triangle comes out like this as a set of combination. So you can see those are symbols of combination, which I walked you through last time we looked at the counting techniques in probability. So binomial expansion makes use of this particular mathematical formula, where you have 1 plus x raised to power n, which is expanded as 1 plus n times x over 1 factorial plus, you can see there, n The next one is a set of n, open brackets, n minus 1.
I'm only seeing the first slide.
Okay, let me just change a bit. Okay, I believe you are able to see.
Yes, sir.
Okay, fine. So I'm trying to walk you through the binomial expansion. This is how it is done. Okay, where you have this relationship as a formula, where you have this particular expression 1 plus x raised to power n. How do you expand it using binomial expansion? So this is what is done when you look at the right side of the equal sign. So that's how it is expanded. If we make use of this type of expansion, then we can look at the next row where you have a plus b raised to power n. How is it expanded? Okay, it will be expanded using this formula on top. It will be, the coefficient will be here 1, that's a raised to power n, then plus n, a raised to power n minus 1, b plus again n minus 1 over 2 factorial, a raised to power n minus 2, b squared, just like that. So that's what is done. So this particular presentation here, if you look at this expansion, is what is being used to expand this particular system of variables, where you have addition here, this expression a plus b raised to power 4. How can we use this binomial expansion to find the answer? So this is where you look at this as pairings. So what you do is, when you look at that, let me just show you what is done here in the next slide. Let's say what you do in this particular case, you look at the power of this particular expression. The power here, or the exponent here is 4. The exponent here is 4. So you do a number of pairings. So you come here, you do a number of pairing. You have AB, again plus again AB, again AB. Since the power is 4, you have 5 of them, AB. So how many are these? AB, AB, that's 2, 3, 4, 5. So that's what we are going to do. So when you look at this, you have 1, you have 2, you have 3, you have 4, you have 5. Okay? So now what happens is that when you come here, the first A, letter A in this particular case, the first letter A in this particular case, you start with the highest power which you have. In this case, you have a 4 here. You have a 4 here. So meaning that the first A times B, the first A in this one, you raise it to power 4. The next A, you will be 4 minus 1. The next A will be 4 minus 2. The next A will be 4 minus 3. The last A will be 4 minus 4. So meaning the power of A will be dropping from A. Here it will be 3, here it will be 2, here it will be 1, here it will be 0. So as the power of A is dropping from A down to 0, the power of B will be rising from 1 to 4. So where you, from 0 to 4. So where you have A raised to power 4, here B will be raised to power 0. Where a here you have a raised to power 3, b will be raised to power 1. Where here you have a raised to power 2, b will also be raised to power 2. Where here a you have raised to power 1, b will be raised to power 3. Where a is raised to power 0 here, b will be raised to power 4. And we know from rules of exponents that any base raised to power 0 is equal to 1. So meaning a raised to power 4, b raised to power 0 means like we are saying a raised to power 4 times 1. Okay? So the last one here we have a raised to power 0 means any number raised to power 0 is 1. It means 1 times it, b which is raised to power 4. Are we together?
Yes.
Okay, so when you look at that type of arrangement in this expression, you are seeing the first a here is raised to power 4. The b here is raised to power 0. The next a here is raised to power 3. The b is raised to power 1. I've just indicated 1 here for the sake of teaching. Any number which is raised to power 1, you don't write 1, you just leave it here. It is assumed there is a 1 there. Are we together?
Yes.
Then a here, which is raised to power 2, b also is raised to power 2. Here a raised to power 1, as I've already explained, b is raised to power 3. Then here a raised to power 0, b is raised to power 4. So any number which is raised to power 0 is 1. Any number raised to power 0 is 1. So meaning that with a here, it will be s to the power 4. b raised to power 4 is 1. 1 times a raised to power 4, it will just remain a raised to power 4. Are we together?
Yes.
Now the idea is that we use the Pascal's triangle to generate the coefficient. A coefficient is a number before a variable. So a and b are variables. So what is the coefficient before a, b? What is the coefficient before this other one? What is the coefficient before this other one? Are we together? So we need to know how to generate these coefficients in the expansion. Are we together?
Yes.
So now, this is when you use the Pascal's triangle. Okay? This is when you use the Pascal's triangle. So we come here. We should have got another one here, which is the next layer, where you are going to have 4C0. Then here will be 4C1. Then here there will be 4C2. Then there will be 4C3. Then last there will be 4C4. Are we together?
Yes.
So the last row will be what I've mentioned. So it expands like that if you are building the Pascal's triangle. So what I've mentioned is what has been used here. You can see here is 4C0. So meaning that this is the combination with n equal to 4, r equal to 0. Okay, so 4 times r is combination of 4 items taken 0 at a time. Then r is 0 and n is 4. Are we together? The next coefficient will be combination of 4 taken 1 at a time. Then you have this particular arrangement. Then a combination of 4 taken 2 at a time. This is the combination. Okay. Here a combination of 4 taken 3 at a time. There are combination of 4 taken 4 at a time. So you calculate this combination. You remember the formula for combination? So the first one will be, I use the first one, it will be if you are looking at, you can write combination this way if you want. The same, if I remember what I told you. Okay, so meaning r is 0, n is 4. So this is the same as 4 factorial.
Both of them, both.
4 factorial 4 factorial divided by open bracket 4 minus 0 close bracket factorial, then 0 factorial. Okay, so that is them. So if you work out this one, it will end up giving you 4 factorial is the same as, you have 4 factorial divided by, the bracket is 4 minus 0 factorial, which simply means again is 4 factorial. Are we together? Okay, 4 factorial. Then multiply by 0 factorial is always 1. So multiply by 1. So if you work out that one, you have 4 factorial as a numerator and 4 factorial denominator crosses each other. So you have 1 on top divided by 1, which is multiplied by 1. Are we together? Which is going to be equal to 1 divided by 1, which is equal to basically 1. Is that okay? Yes. So that's how you resolve that one. So you find that in this case, the first combination, this one, the coefficient to give is the one here which I've worked out. Is that okay?
Yes.
So then you put 1 multiplied by a to the power 4 times b to the power 0. This is the expression you are seeing here.
Okay.
Okay. Then you have the next one. You find a combination of 4 items taken one at a time. So when you work out this combination like the way I've demonstrated, you'll find that it will give you 4 as a coefficient. So coefficient 4 before a raised to power 3 and b to the power 1. This is the expression you are seeing here. Are we together? You go to the next one. Combination of 4 items taken 2 at a time. When you work out this combination to give you 6, this 6 here. So which is this 6 coming before a squared b squared. That's what you are seeing here. Then the next one, this combination of 4 items taken 3 at a time. When you work it out, you find that it will be again 4 here. This will be giving you 4. So 4 times a times b cubed. That's what you are seeing here. The last one, this is a combination of 4 items taken 4 at a time to give you 1, which is 1 times a raised to power 0 times b raised to power 4. So if you simplify this row, it will end up 1 times a to the power 4 is a to the power 4. Then plus 4 times b raised to power 4 times a raised to power 3 multiplied by b. This is the one. The next one will be 6 times a raised to power 2 times b raised to power 2. Then plus this one will be 4 multiplied by a multiplied by b raised to power 3. The last one will be 1 multiplied by, again this a raised to power 0 is 1. So it's the same as saying 1 times 1 times b to the power 4. This is what gives you this one here. So it means that you have done the expansion. So the expansion of a plus b to the power 4 is equal to this, using the binomial expansion. Are we together?
Yes, sir.
Okay, that's how you expand using that. So we have used combination in this formula. So that's what Blaise Pascal used. Okay, about 1600 years ago. He was formulating this in the 1600s, somewhere there. So a long time ago. So you can see that. Okay. So now, just as a matter of exercise, so this is what you have here. Okay, this is what you have here. So we can try this one so that we demonstrate how that is done. Is that okay? The
Yes.
first one here. Okay. So let's look at this first one. What we have in this particular case, we have x plus 9 raised power 3. So expand this using binomial expansion. So how many items are here? Is x 9 times 9. Are we together? And then
Yes.
the power is 3. So meaning that in a similar manner, like this one, you are going to have, instead of a, you have x here, and here you have 9. Okay, you have x here, and here you have 9. You have x here. Just simplify this one. So basically, this is what you have to line up. Like that. Okay? So here you have what? You have a plus. So in between, you put plus. And here in between, you put plus. In here in between, you put plus. In here in between, you put plus. You see that? Okay. So instead of AB, we have X9. Okay. Then we use the Pascal's triangle to determine what coefficients will be coming before these. Okay. So you come here. Since they are 3, the power is 3, then you go for the last one, which starts with 3 here. So there will be 4 coefficients. Are we together?
Yes.
Okay, so you come here. So the first one will be the first one here will be 3, then capital letter C, then 0. Okay, that's a coefficient. And then the next one will be 3, capital letter C, then you have 1. Okay, the next one will be 3, capital letter C, then you have 2. The next one will be 3, capital letter C, and you have 3, 0, 1, 2, 3. Have I left one? 0, 1, 3, yes. 1, 2, 3, 4. Yes, this is the last one. So you have 3 here. Okay? Are we together? So meaning
Yes.
that this one shouldn't be there. Okay, like that. Okay. So now you find this one. You start. When you have this, okay? So now this x should start with the highest order. The order of this particular expression is 3. So it's raised to power 3. Let me just look at that. Let me just look at that.
Yes, Messi. How are you?
I
How are
meant
you,
to put.
Not bad, thank you. Talk to me now.
Okay. Okay. So x raised power 3. Then this one.
No. So how are you going to do it?
This will be 9
Oh. So how do you want to send your...
raised power 0.
Oh, from the phone?
0. The next
And
one.
the Moodle is not possible. No, use the WhatsApp then.
Will be.
Use the WhatsApp. Yeah, then you can send it on your WhatsApp.
Okay. So this one here, the power of x will reduce by 1, so it will be 2, and this one will rise by 1. There will be 1 here. Are we following?
Yes, sir.
Then the next one will have this one. So in this case, x will further drop by 1. So it will be 1 here. And then 9 will further rise by 1. So it will be 2 there. Then finally, we have here x will drop by further 1. So it will end up being 0 here. Then 9 will raise by another 1, it will be 3 there. Let me just increase it. Okay. So what do we have? Now we have to work out the coefficient. Okay. So when you calculate the combination for the first one, it will give you 1. Are we together?
Yes.
So it will be 1 times x raised power 3 times 9 raised power 0. Okay. The next one, it is 3 factorial divided by 3 minus 1 factorial. So everything factorial, then times 1 factorial, the correcting factor. Okay, so this means that you are going to have 3 factorial divided by 2 factorial multiplied by 1 factorial. Okay, so if you simplify that, 3 factorial simply means 3 times 2 times 1, which is divided by 2 factorial simply means 2 times 1. Then 1 factorial simply means times 1. 1 factorial is always 1. Is that okay?
Yes.
So when you simplify that, it simply means 6 divided by 2, which is equal to 3. Do you see that?
Yes.
Okay. So meaning that this one will become 3. The coefficient when you resolve that one, it will be 3. All together?
Yes.
So the next one, you look at this one, it will be 3 factorial. The R has changed to 2. Are you seeing? So there will be 2 here. Okay. Then 2 factorial. Okay. Okay. Which is simply means 3 factorial divided by 3 minus 2 is 1. So it will be 1 factorial here. Then times 2 factorial. All together?
Yes.
So apparently it will be the same as this one. So that what will swap here is the denominator. Here it will be 1. Here it will be 2 times 1. So it will still be 6 over 2, which is equal to 3. Are we together?
Yes.
So means that the coefficient here will be again be 3. Okay. Then when you work out this one, it will be 3 factorial divided by 3 minus 3 factorial, then 3 factorial. The correcting factor 3 factorial, because R is now 3. Are we together?
Yes, sir.
Meaning that this one will be 0. 3 minus 3 is 0 factorial. Then this one will be 3 factorial. So it will mean that you have 3 times 2 times 1, which is 3 factorial, the numerator, divided by 0 factorial is 1. 0 factorial is 1. So there will be 1 there times. Then 3 factorial is 3 times 2 times 1. All together?
Yes,
So when
sir.
you work out this one, it will be 6 divided by 6,
Yes.
which is going to be equal to 1. You see that, huh?
Yes.
Meaning the last coefficient here, it will be 1. All together?
Yes, sir.
So now, if I remove that, I simplify this one. What does it give me?
Nine.
Simplify this one. It means that this one won't change anything. Means that this one, any number raised to power 0 is 1. So it means that this one is the same as you are multiplying by 1. You are multiplying by 1. Okay. So multiplying by 1. Then this one, x squared times 9. This one will be 3 times x squared times 9 to the power 1. This is 1. It will still be 1 here. Then here, 3 times x to the power 1. So x to the power 1, we don't normally put the... When there's 1 there, it's taken that's that. Then any number raised to power 0 is 1, so it's like saying here 1 times 1. Okay, then times 9 times 3. Okay, So that's what we have here. Okay, that's what we have here. Okay. So when we resolve this, what are we going to have? This one will simply be 1 times x to the power 3 times 1. It will be x to the power 3. Then come here. 3 times x to the power 2 times 9. So it will be 3 times x times 3 times 9, which is 27. Are we together?
Yes, sir.
So it will be just 27. We have already multiplied this 9. It will be 27x to the raised power 2. Then here we have 3 times x times 3 times x times 9 squared. Okay, it will be, we are multiplying, first of all, 9 squared is 81. Then multiply by 3. So in 81 times 3, times 3. You are going to get 243. You are going to get 243. So meaning this one, you multiply that one by 81, it will be 243x. Then resolve this one. 1 times 1 is still be 1.
So
Okay, times that, it will be that. Remember, 1 times 1 times 9 to the power 3. That will be, if you look at that, 9 times 9 times 9, which is equal to 729. This one will all reduce to 729. 729. Okay? So that's what we have. That's what we have. Okay? So now, this is the of higher order x cubed. This one is lower order x squared. This one is lower order x to the power 1 and 29. So we cannot simplify further. It means that the expansion will end here. Is that okay?
Yes, sir.
Okay, that's how you expand using binomial theorem. Is that clear?
Yes, it is.
Okay, so you can look at these others and see how you can try to resolve them in a similar manner. So that's how you do the expansion. Meaning that here you have 4 pairs of x9. Here you have also 4 pairs of 2x times 2. Then you're going to have 6 pairs of AB, 6 of them because the power is 5. You just increase the pairings by 1 more order of what the power it is raised to. So like you can hear the first one we've been dealing with, we increased to 4 pairings. Is that okay? X9, 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 4 of them. Because the power here is 3. Here it will be 2x2, 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 4 of them. Here it will be 6. AB, 6 of them. Just like that. Here it will be W over 2, 1, W over 2, 1, 4 of them. Just like that. Here it will be 3. X2, x2, x2. Is that okay? Then you do the expansion using those Pascal's triangle. That's how you do it. Okay. So that's the binomial expansion. So I challenge you to work on this one yourself. See whether you can be in a position to manage them.
Is that one?
Okay. Are we together?
Yes, sir.
Okay, fine.
I'm just
So now,
to wind up on these CAs.
I look at the other one, which is an illustration
Did you send your
to do with a random sample of size 3. Was taken from a large batch of components which were classified as defective for D or non-defective for N. Okay, then you have found that let the probability of item being defective equal to P, the probability of item being non-defective equal to Q. Okay?
Are you able to send it?
So in this particular case, we have probability of defective equal to P, probability of non-defective equal to Q, which is the complementarity of the first one, which will be 1 minus Q, 1 as P.
Please send it
That
now.
is what we have. The sample space can be found by N raised per R.
Thank you.
Okay? So now, how many possible outcomes do we have? We have 2, either defective or non-defective. Are we together?
Yes.
Okay. How many? We have been told the samples, the random sample of size 3. So, random sample of size 3. So, the 2 possible outcomes, the base, the sample size 3 is the power. So, meaning that if you want to know the sample space, you can use this formula, 2 raised power 3 with the sample size to give you 8. Meaning there are 8 possible outcomes. That's the sample space. So that's what I want to show you here. You want to determine the sample space, given this arrangement, you can calculate it. Okay, so that's what we do. So going further, we look at this and it will show you how many possible outcomes. There are 8 as we are calculated here. Sample space is 8. So we have 8 because the random size is 3. So we can have this one where you have the first one is non-defective, the second one is non-defective, the third one is non-defective. Okay, it can be again the possible. You can non-defective, non-defective, defective. You can have non-defective, defective, non-defective. You can have defective, non-defective, non-defective until you get defective, defective, defective. So the possible outcomes are these here, sample outcomes. There are 8 of them, as evidenced by this calculation to guide you that this type of situation you are going to have 8 possible outcomes, which you call sample space. If the probability defined, the probability of defective is P, the probability of non-defective is Q, then we can work them out in this manner to say, if the n, then is Q times Q times Q, because it means that non-defective followed by non-defective followed by non-defective. I did mention earlier on in my presentation that when probability is indicating that an outcome is following another one, then the probability of the 2 outcomes or the outcome is supposed to be multiplied. So as it indicates followed by, then you have to multiply the probability. So you multiply the probability of first outcome n, which is Q, by second outcome n, which is Q, and third outcome n, which is Q, giving you Q cubed. The next one, you have possibility that you can have non-defective followed by non-defective followed by defective. So you have Q times Q times P, which is Q squared P. The other one is possible that you can have non-defective, defective, and non-defective. Means that you have Q times P times Q, which is still the Q squared P. The other one you have defective, non-defective, non-defective, which is going to give you Q squared P. Until we reach the last one, which is defective, 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 which is P times P times P, which is P cubed. So these are probabilities you calculate. Are we together?
Yes, sir.
Okay, fine. So now, when you look at that, okay, when you look at that, we can now use the binomial probability distribution to calculate the probabilities as indicated above in the illustration. So let's go back and see how this was done. So in the first case, we are looking at the probability of one defective. Probability of one defective. One defective comes here. Whether it's one defective, 1D, is either this one or this one. Okay? This one or this one. So what is the probability of non-defective? We ended up having Q cubed P. Okay? So Q cubed P. So how do we do it under binomial expansion? Okay, we have come here. We are given probability one defective is equal to P squared Q plus P squared Q plus P squared Q, which is the 3Q squared P. Okay, which is the same as out of the possible 3 trials, one is defective, one is taken to be defective. That's what it means. So you are going to find a combination of 3 elements taken one at a time, which is defective. Okay, are we together?
Yes, sir.
So that's what we have here. So meaning that the first one will be 3Q raised to power 3 minus 1. Okay. Then the next one will be P raised to power 1. Okay. So when you work out that one to give you 3Q raised to power 2, when you simplify that, P raised to power 1. That's what it would be like. Okay? 2 defective in a similar manner, means that 2 taken out of 3 trials or 3 elements, 2 are defective, means that 3 elements taken 2 at a time. Then what you do is you just look at the highest order. In this particular case, you will subtract by 1. Then the next one takes the next item, which is 2 here, raised to power 2. Okay? So that's what happens in this particular case. 3 defective, so means 3 at a time. 3 items taken 3 at a time. So it will be combination of 3 items taken 3 at a time. You are going to have Q raised to power this 3 minus R, which is 3 here. Then the next one raised to power R, which is P raised to power 3. So it will be, this one will be going to be 0 here. And then this one raised to power 3. Q raised to power 3. P raised to power 3. Okay. Then when you have probability of 0 defective, so 0 taken at a time to be combination of 3 items taken 0 at a time. So you have the first power, which is 3, to which Q is raised, minus 0 here. Okay, then the next probability is which is P raised to power 0, the same. So then you're going to end up with this, which is Q cubed. Because 1 times Q cubed times 1, it will be Q cubed. So this is how the binomial distribution probability is worked out. So from this generality, we have a formula which helps us to determine the binomial probability. So from this explanation, we have the formula, which is the general formula, which can be summed up as follows. What we've done here is what is summed in the general formula here. So for you to find the probability X, where you are given this particular formula and the general formula, you have X, possible outcomes N, taken X at a time, where the probability of two outcomes is known, probability success P, and probability failure Q is known. So where P is the probability of success in a single trial and Q is the probability of failure in a single trial. So this is the general formula which is given under binomial distribution. Okay, so we are going to make use of this formula whenever we calculate the binomial problem. Whenever we calculate the binomial problem. So let's look at an example, okay, to help us ride on it. Okay. Example, you are given that suppose you have a pack of cards which is cut 5 times. Okay, so how many trials? There are 5 trials. Okay, being shuffled between each card and no card actually removed, because there are cards which are shuffled without with replacement, should I say. So there is no card which is being removed. Then the probability of cutting 0, 1, 2, 3, 4, and 5 spades is given as follows. Okay, so now what is the position here? We are looking at an event. Event E is the suit of cards shown. Okay, and the probability success is obtaining a spade. So the probability success for obtaining a spade is, as we know, we can say it is Q. Okay, we can say is Q. Okay, that's probability. So if you look at the card, okay, you look at the card, the deck of cards, what is the chance that you draw a spade? How many spades are in a deck of cards? That's what the question we're supposed to ask ourselves. Okay, and how many cards are there? That's another question we have to ask ourselves. Okay, so if I'm not mistaken, there are 52 cards and there are 13 spade cards. Okay, so what we have here is find first of all the probability of spade. Probability of a spade, as I've said, there are 13 spades if you are familiar with cards, and the total number of playing cards are 52. Meaning that the probability success is 13 out of the possible 52 cards, which simplifies to 1 over 4. Because there are 13 goes into 52 4 times. So to simplify this one to be 1 over 4, which is likened to probability Q. So probability Q, or probability drawing a spade, is 1/4 or 0.25. That's what it means here. Now means that the probability of not drawing a spade, any other cards, means that the difference, which will be 39 over 52. So if you remove 13 from 52, you remain with 39. So the probability of not drawing a spade is the total possible outcome 39 over the total cards 52. Again, which gives you 3 out of 4 or 0.75. Okay, in this case. So we have the two possible outcomes whose probabilities are known or can be calculated. We can calculate the probability of spade, which is 1 over 4. We can calculate of drawing not a spade, which is 3 over 4. Okay, and there are two possible outcomes. Either you draw a spade or not a spade. Means that is a binomial problem. So if we know the two probabilities, then we can slot it in the general formula to find the probability. This general formula. Okay, that's what we're going to use. Okay, we can slot in the general formula to find the probability. Okay, so the general formula, we start looking at calculating these probabilities probability of drawing a 0, probability of drawing a 1, probability of drawing a 2, a 3, a 4, and up to 5. So that's what we start looking at. So what is the probability of drawing a 0 spade? So it will be in the general formula. You are going to have combination of 5 taken 0 at a time. Okay, 5 taken 0 at a time. Then this is 1 over 4 raised power 0. Okay, and then 3 over 4 raised power 5 minus 0. So look at the general formula. So the probability success takes the R. Probability failure takes N minus R. So that's what we are following. Are we clear?
Yes.
Okay. So that's what we are seeing here. So probability that we take 0 spade. So it means we are going to use this combination here, and then you have the first probability of drawing a spade is 1 over 4, which is 13 over 52, raised power 0, taking after this R here. Okay. Then the next probability of failure is 39 over 52, which is 3 over 4. Then that is taken to be raised power 5 minus 0. That's what you are seeing here. Are we together?
Yes, sir.
To simplify this one, the combination, the first one, this combination simplifies to 1. If you work out that one, the combination will be 1. Okay? Then times 1 over 4 raised power 0. Any number raised power 0 is 1. Are we together? Then
Yes,
the
sir.
next one is 3 over 4 times 5 minus 0 simply means is the first one is 1. Then this one times 1. Then next one times 3 over 4 raised power 5. That's what it means. Are we together? So if you work out this one, it will simplify to 0.23730. That's the probability of drawing a 0 spade. Are we together?
Yes, sir.
Probability of drawing 1 spade. Okay, you have 5 possible experiments. Shuffling, because when you shuffle, it's more like an experiment. It's a try. You cut, means that you pick a card. Okay, so you are going to shuffle 5 times. That's why N is going 9. The number of experiments, there are 5. Okay, you take 1 at a time. You provide that to get 1. This is what you're going to show here, the probability, the coefficient. Okay, so now again in a similar manner, the X here is the power you raise to the probability success, which is 1 over 4. Is that okay?
Yes, sir.
Then probability failure that you don't draw a spade is 3 over 4 raised power 5 minus 1. Okay, so when you simplify this one like before, you end up having with this arrangement here. And when you simplify that one, it will end up giving you 0.39550. That's the probability of drawing 1 spade in 5 trials.
Okay.
Okay? So again, you move on to find the probability of drawing 2 spades in 5 trials. It will be the same. You use the general formula, you slot in, you find this. Until you reach where you probability of drawing 5 spades, it will be 0.0097. Are we together?
Yes, ma'am.
Okay. So if you want to counter check whether the calculations are right or not, you add the probability of drawing a 0 spade from the beginning here, which is this one, plus the probability of drawing a 1 spade, which is this one, plus the probability of drawing 2 spade, which is this one, probability of drawing 3 spade, this one, 4, this one, 5, this one. When you add, they should come to 1, because the sum of probability of outcomes is 1. Okay? Okay,
Yes,
fine.
sir.
So you don't need to do that. All you need is remember the formula and then slot in and find the probability. But if you have time to just check at a leisure time, you can add them, you find that you come to 1.
Okay.
So that's how you calculate the probability when you have a binomial distribution. Okay, so having looked at that, I want to talk about the features of a binomial distribution. When we talk about features, we are talking about characteristics of binomial distribution, or elements of binomial distribution, or attributes of binomial distribution. Is one and the same thing. What are these things that we identify with a binomial distribution in short? There are a number of them. One of them that an event has only two recognizable outcomes, like the questions we have looked at. Okay, either you draw a spade or you don't draw a spade. There are two possible outcomes. Either you like a candidate or you don't like a candidate. Either in the inspection, quality inspection exercise, the product is defective or it's not defective. So such type of situations are referred to as binomial distribution problems. So that's why A is talking about an event has only two recognizable outcomes. The second one is that the probability of two outcomes can be calculated. So we saw that the probability of drawing a spade is 1/4. The probability of not drawing a card which is not a spade is 3/4. So the probability of these two possible outcomes can be calculated. Then it's a binomial distribution problem. C. The values of the probability remain constant throughout the experiment. So the assumption that the values of the probability remain constant throughout the experiment. Okay, that's what you should know. Again, here we are saying that it is applicable to discrete variables. Okay, it is applicable to discrete variables. What are discrete variables? Those variables which occur in jumps, like counting numbers. Those are discrete variables. Okay. So then we have the mean, which is represented by a Greek letter mu, which is calculated as n times p. Okay. Number of elements times the probability success, that gives you the mean. Okay, number of elements times probability success, that gives you the mean. Okay, so for instance, in this regard, for the experiment involving 5 trials where you are trying to get probability success a spade and the probability failure a non-spade, probability success a spade is 1/4. How many trials are there? There are 5. So the mean, you multiply 5 times 1/4 or 0.25. That will give you the mean. Okay. So now, this one bigger. A bit down so that you can see. Okay, at least you can see something there.
Yes.
Okay, we have this type of arrangement. Okay, you are told that it's an example. Let's put this one. You able to see something?
Yes, sir.
Okay, fine. So I'm giving you an example on how you can calculate some of these particular issues. Okay, we have, for instance, how do we calculate the mean? As I've said, Given they have 1,000 tosses, mean that n is 1,000 of a fair coin. A fair coin. Determine the following probability, the mean. But particular about the mean. So we have n is 1,000. The probability of success of, for instance, a head is 1 and 1 out of 2. So if you are trying to get a head, okay, it will be 1 out of possible outcomes 2, which is head and tail 2. So to find the mean, you simply multiply n times p. So 1,000 is n times the p, which is probability success half, which is going to be 500. Meaning the mean in this case will be 500. If you want to find the variance, you can get the formula is sigma squared, or theta squared times npq. So the n is 1,000. Probability of success is half. Probability of failure for this particular fair coin is half. So it would be 1,000 times half, which is 250. If you want to find the variance, you find the square root of theta squared. So square root of 250, that will be the variance. So that's what is of interest for me. Just in case you wanted to experiment looking at these particular parameters which you need to calculate. Otherwise, my interest was looking at binomial distribution. Okay, binomial distribution. Are we together?
Yes,
Is that
sir.
clear?
Yes.
Okay, so that's where I want to end. So I've shown you how to apply the binomial distribution formula, general formula, and how to calculate the probability of a binomial problem. So those features which I talked about are the ones which are going to help you when you're looking at the challenge before you. Find out or look out for those features for you to decide whether it's a binomial problem or not. Next time we meet, we are going to look at Poisson distribution. Again, there are features that we are going to look at which will make you understand that you are dealing with a Poisson distribution, not a binomial problem. So that's what we are looking at.
Okay.
Thank you for listening. I hope to meet you again tomorrow and look at Poisson distribution.
Okay, sir. Looking forward to it.
We're
Great.
on the phone. You didn't